the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through LU factorization. I actually had done 2 videos prior to this, and I went through the process of LU factorization already, so you should have already familiarized yourself with that process. However, I did not actually do a full example of just solving a matrix equation using LU factorization, so I thought I'd have this addendum video for that process specifically. Again, I'm assuming that you know the LU factorization process now, so I am going to use a lot of the tricks that we developed in the previous video to help me solve this matrix equation. Speaking of which, solve the equations ax equals b and ax equals c using LU factorization, where the matrix A is this 4x4 right here, and then B and C are those vectors right there. As I've mentioned in the previous videos in this series, you can solve a matrix equation like ax equals b using row reduction. Of course, there is an issue if later on somebody comes in and says, oops, I forgot to tell you I have a different right-hand side I'd like you to solve that same equation for. In that case, row reduction is actually pretty costly as far as computations go. The other method that we have to solve these equations is by using the inverse. If A is invertible, then you know that X is equal to A inverse B. Likewise, you could use the inverse to solve this equation. You'd get X is equal to A inverse C. Now there's a big conversation to be had about when you should use one method over another. And part of that conversation is knowing beforehand, did somebody hand you these right-hand side vectors simultaneously? In other words, if you walk in a room and you know you have a constant coefficient matrix A that will never change, but you're handed initially maybe 2, 3, or 4 different right-hand side vectors. Now, notice what I just said there, that you were initially handed those. So you walk in the room, somebody says, hey, I have an equation involving the matrix A. It's AX equals something. The something is either B, C, D, or E. It's one of these 4 vectors. Well, in that case, with a 4x4 matrix, you actually would spend more time finding the inverse than you would if you had just augmented the matrix A with those 4 vectors that somebody showed up with. Now, this is somewhat of an abusive notation, but the fact is, it's sort of like you're saying, I was going to solve AX equals B, but I also want to solve AX equals C, and I want to solve AX equals D, and simultaneously, I'd like to solve AX equals E. These are 4-column vectors, and all your row operations that you'll use on A will affect each of those vectors simultaneously. And if you use the row reduction algorithm appropriately to get it into reduced row echelon form, the matrix A that is, then in that process, you'll find the corresponding solutions to each of those equations, and they would be like this. You would have the identity matrix because you used row reduction to get A into reduced row echelon form, assuming, by the way, that A is invertible. And those right-hand side vectors through all of those row operations become the solutions you are looking for. Well, I mentioned that this is worthwhile to do if you have been given up to 4 right-hand side vectors, 4 different right-hand side vectors. And the reason why I say that is because this is a 4x4 matrix. Your other option is to initially find the inverse of A. However, finding the inverse of A means you're augmenting A with the identity matrix, and that identity matrix has 4 columns. So it's basically the same thing as this. However, when you find A inverse through row operations, those same exact row operations that would take this A and change this into the identity matrix and simultaneously give you these 4 solutions. Well, if you did that over here, you would have A inverse, but you wouldn't have your solutions yet. You'd still have to multiply that A inverse against each of your given right-hand side vectors, B, C, D, and E. So you can see that there is a little bit of a thought process involved in which method to choose to solve a matrix equation if you have multiple right-hand side vectors. It just depends. If you walk in a room and somebody says, by the way, this coefficient matrix A is never going to change in the future. However, I'm also never going to hand you any other right-hand side vectors other than these 4, then I probably wouldn't find the inverse matrix, because they're promising me that I'm only ever going to see these 4 right-hand side vectors. There's no need for me to find the permanent inverse there. However, if I walk in the room and they say, hey, I've got a couple matrix equations, they both involve the matrix A, so it's AX equals B, and the other one is AX equals C, and they say, could you please solve these? My first question would be, well, is it possibly the case that tomorrow I'm going to come in and you're going to hand me a completely different vector for the right-hand side? If they say, oh yeah, that's a possibility, then I wouldn't bother using this augmented matrix. Instead, I would go ahead and find the inverse matrix, because then whatever they hand me tomorrow, I will just multiply that vector by A inverse. Now we're in a situation where we have a new factorization method, and it's the hybrid of these two. If we walk in a room and they've handed us multiple right-hand side vectors immediately, I would probably use the LU factorization algorithm. Maybe not always, but I probably would consider it. Likewise, if they told me, by the way, maybe tomorrow I'll give you some different right-hand side vectors, again, I would probably heavily consider the LU factorization algorithm. I tell you this because you might be going into a career or into a field that involves numerical analysis or solving large systems, and to do so, you have to make these decisions. I want speedy computations without error. Or you might be willing to accept a little bit of error in your computations to really speed up things. And those are fairly advanced techniques, like a conjugate gradient method or something like that, which is not the purview of this course. So let's get this off the screen and let's go ahead and start the LU factorization. Remember, to do an LU factorization, we are just going to treat it like it's a regular matrix A and that we're doing some row reduction on it. So let's go ahead and make a few mentions here. Right at the get-go, you always, with an LU factorization, you start with the upper leftmost pivot, you highlight that entire column, and you start to build L. And the way you'll do that is you'll look at that column and you'll divide the entire column by the value of the pivot. So you're going to divide the entire column by a -2. So you get 1, -1, -5, and 3. Now remember, L is a lower triangular matrix. So what I'm going to do is just fill out the rest of the entries where I know we're going to have 0s and 1s. And I should also say that L will always have 1s along the main diagonal. All right, that being done, and we almost have L filled out, honestly, we'll go ahead and use some row reduction techniques. The nice thing about row reduction techniques is that you are on purpose choosing sums so that it kills off everything below your current pivot, so you don't have any computations there. Now, performing these row operations on the remaining submatrix here, I'll go ahead and do that right now. Barring any arithmetic mistakes, that should be correct. Now you can see I have a new available pivot here. I'll highlight that pivot in all entries below it, and then I'm going to go ahead and divide those values by the value of the pivot. And that would give me 1, 2, and 8. And that will be these entries right here, 1, 2, and 8. And you can see that fills out very nicely. Now let's go ahead and continue forward by continuing to find the matrix U here, or the echelon form of A. Notice again, I will have a nice clean submatrix where all my computations are actually going to occur, because everywhere else is 0 by design or has already been computed, which is all this stuff I circled up. All that stuff has already been computed. We're done working on it. And this stuff down here is 0 by design. So really, we're only doing math on this little sub matrix. So let's do that, mathematics. All right, and you can see I used blue this time to showcase that that's what I computed in this step. And that's where all my computations occurred. Now you can see that again, we have another pivot that just appeared. And I'll go ahead and highlight that pivot and everything below it, all the entries below it. And since that pivot's already a 1, I can go ahead and in my matrix L, insert 1 and 6 as those elements there. 1's already there, but I want the -6 in there. So we have now found L completely, and we're almost done finding U. The only entry that we really have to compute is this entry right here. We'll just take 6 times row 3 and add it to that row, and there we get our answer, or at least our matrix U. I'm just going to quickly look through and make sure I didn't make any arithmetic mistakes. And I actually found one. Now, I did that not on purpose. Honestly, that was an accident. That's just how it works. But I found that, or I knew I should probably look, because of the fact that you're doing a lot of arithmetic, and we take arithmetic for granted. We do happen to make a lot of mistakes because we're human, and so that's exactly what I did there. I made a little silly mistake. Now that does not affect my -6 in my lower triangular matrix L. However, it does affect a small computation in my next step. So let me fix that as well. All right. Very, very good idea to check your arithmetic when everything's said and done, because there are times when you can make a mistake. Also, by the way, it is the case, I see it on my exams that I give to my students, that when you make a mistake, if you can't find that mistake within, let's say, 30 seconds of glancing through your work, it's almost better to restart your work. Just because if you don't see it within 30 seconds, you're likely never going to see it. Anyhow, we now have L and U, and we want to solve AX equals B and AX equals C. Well, remember, A is L times U, and we want to solve those two equations right there. And if you recall from the first video in the series, this would be the same as solving these two equations, where ux sub 1 equals y sub 1 and ux sub 2 equals y sub 2. And I thought I'd use subscripts here because we have two different solutions. So I'll call those x sub 1 and x sub 2 up there as well. So people often look at this and say, wait, you mean I have to solve two different equations to solve this one equation? And I have to do LU factorization on top of it? This just sounds like too much work. It actually is not. There's something really glorious that happens when you do this. Now, before we dive into actually solving Ly is equal to B and Ly is equal to C, I want to show you something very special about solving a matrix equation where your matrix is a lower triangular matrix like L, where the entries along the main diagonal are 1. This is, I'm just going to do it via an example, a smaller example. So this is not going to be the L that we had up above, but let's pretend as though the L that we were given is the following. And let's suppose that the right-hand side vector, B, is the following. If I'm going to solve that matrix equation, in this case, Lx equals B, you can see the row operations. We'll just add row 1 to row 2. And by design, there's no math behind this. By design, that -1 will become a 0. However, 0 plus 1, well, that's still a 1. 0 plus 0, that's still a 0. In other words, nothing else changes in the second row of the coefficient matrix because everything above those entries are zeros. However, we still do have to add 1 to 0 here to get 1. Our next move is to take -2 times row 1 and add it to row 3. When you do that, again, in row 1, at least of the coefficient matrix, there's zeros everywhere except for the first entry. So the only thing that's going to change is the first entry in row 3. And we know what that's going to change to. By design, it will become a 0. So again, the only mathematics that we need to do is the mathematics of -2 times the 1 up there plus 6. Finally, I'm going to go ahead and take -3 times row 2 and add it to row 3. Again, look at row 2 of the coefficient matrix. There's zeros everywhere except for in that middle position. So the only thing that's going to change in row 3 is the middle number. And by design, we know that's always going to just change to 0 because we're forcing it. But we still have a little computation over here. -3 times 1 is -3 plus 4 is 1. And look at this. We have found the solution, and the only mathematics we needed to perform occurred in that augmentation column. So why did I bring up this side example? Because that's what we're going to do with our current example. I'll go back up here. What we're going to do is take this matrix L and augment it with B and actually with C. I'm going to do it simultaneously. And in reality, you don't even have to do that. You could read off how you're going to do this. So watch how I do this. I'll do this, maybe I'll do this down here. All right, so these are the two vectors, the right-hand side vectors we're dealing with in these equations right here. The Ly sub 1 is equal to B and Ly sub 2 is equal to C. Now we know that when, just from the example I just gave, that when we do row reduction on this matrix L, all we're doing is really just keeping track of, well, I'm adding row 1 to row 2. Then I'm going to add 5 row 1 to row 3. Then I'm going to take -3 times row 1 and add it to row 4. And we only have to do that mathematics on the actual right-hand side vectors. So let's go ahead and list out the moves. Actually, I should have just kept those arrows, but let's list out the moves here. Row 1 plus row 2. Let's go ahead and at least do that. I'm not filling out the rest because I'm going to do all of these in the same fell swoop, or at least all the first column moves. So the next set of moves is this one right here. Again, we said it earlier, but it's 5 times row 1 plus row 3. So going back down to our vectors here, I'll take 5 times row 1 and add it to row 3. Now let's go ahead and go back up and deal with rows 1 and 4. -3 times row 1, we'll add that to row 4. Let's go ahead and do that in those vectors. So let's see, -3 times this row and add it to that row. All right, so that's our first column manipulations. Now we go to our second column manipulations. I'm going to take -2 row 2 and add it to row 3. And I might as well just say this simultaneously. I'm also going to take -8 row 2 and add it to row 4. That should kill off those elements. So -2 row 2 added to row 3. And let's see, what was the other one? -8 times row 2 and add it to row 4. So -8 times row 2 and add it to row 4. Again, watch out for arithmetic mistakes. They can occur quite frequently here. Hopefully I'm not making any. And now I'm going to go ahead and erase all this stuff and deal with the final move. 6 of these row 3s, add them to row 4. Let's see what that looks like down here. 6 of these adds to row 4. And I just spent a little bit of time checking my arithmetic. I think we're okay. So what do those represent? They represent the right-hand sides after we've augmented L with B and done row reduction techniques. That B will change into our solution, y sub 1. So we know that y sub 1 is this first column, y sub 2 is the second column. Now I talked my way through quite a bit of that, but the reality is it's much faster if you're not talking and you just do it. Now we're going to go ahead and go through and solve ux sub 1 is equal to y sub 1 and ux sub 2 is equal to y sub 2. Now I'd like to take a moment before we continue and just say that usually this is a low-level computer science programming problem. Like when you're taking a programming course, this is like one of the early coding projects you go through. build a program that would solve a system of equations using LU factorization. So there is a way to code this. In fact, if you search the internet for LU factorization, the first few pages are just a bunch of algorithms written, a lot of codes written by computer science folks and programmers. So anyhow, we just need to take this upper triangular matrix, augment it with those two right-hand sides, and solve. And I will do this again in one fell swoop. I'll take the upper triangular matrix and I'll double augment it. I'll augment it with y sub 1 and with y sub 2. That way I'm just solving for both x1 and x2 simultaneously. It's the same row operations, so I don't want to have to repeat this process. So let's do this. Dividing row 4 by 4. Well, I'm just going to do that. In fact, I'll probably use this matrix and the fact that I have a digital whiteboard to really do a lot of my mathematics. So the next one I'm going to perform is -7 times row 4, adding that to row 3. Now the danger of doing this with a sheet of paper is that you'll lose all of your computations. So I wouldn't do this using a sheet of paper, but a digital whiteboard is actually kind of nice to do it with, although you still lose all your calculations. Now I'm going to take row 4 and add it to row 2 to become the new row 2. Now I will take -3 times row 4 and add it to row 1 to become the new row 1. Then I move on to my next pivot, which is luckily a 1. Negative row 3 plus row 2 becomes the new row 2. -2 row 3 plus row 1 becomes the new row 1. And that completes that column. Now we go to the next pivot, and you can see that pivot needs to be divided by a -3. Now we'll take the opposite of row 2 and add it to row 1 to become the new row 1. And finally, we'll divide row 1 by a -2. And you could see that our solutions, x1 and x2, are 0, 1, 1, 1, and 2, 1, 0, -1 respectively. Those are the solutions to ax equals b. It's technically ax sub 1 is equal to b, and ax sub 2 is equal to c. Note the trick I used for L again. L just tells me what moves I'm going to make on my vectors when I'm solving an equation. So I'm going to add row 1 to row 2. I'm going to add 5 times row 1 to row 3, and I'm going to add a -3 times row 1 to row 4. And I only do that really in the vectors because by design, this is just going to change to the identity matrix, and all of those operations don't touch any of these other numbers. Likewise, and I didn't make a big stink of it because, well, normally I just don't bother, but likewise, that same argument holds for the upper triangular matrix. And you can experiment with that. I'm just not going to bother. I just wanted to get you an extra example here on how to solve a system of equations using LU factorization. I hope this video is enlightening, and I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.